We are cadets Paul Chau, Coral Howell, and Owen Putnam. We are from the United States Military Academy at West Point, New York. Our sponsor is Major Ivan Bermudez. We are Team 1067. We chose Prompt B. How does AI model collapse occur? When AI models are recursively trained on data generated by previous models, it's observed that outlying data is removed each generation, eventually leading to model collapse. Model collapse occurs when this recursive sampling causes the model to completely lose variance, resulting in a single point distribution. Our three questions to analyze are: will the quality of AI model results dramatically decline, slowly decline, or remain unaffected? Can human data slow, stop, or reverse the rate of collapse? And what is the role of multiple AI models interacting with each other's outputs? For our approach, we developed three differential equation models representing distinct training conditions for AI models. Model 1 simulates a fully self-trained AI. Model 2 introduces the preservation of human data. And Model 3 introduces the interaction between multiple AIs. Perplexity quantifies how surprised an AI model is by new data. The higher the value, the more inconsistent the data. If we assume that all data follows a Gaussian distribution, we can model how the mean and variance evolve across generations. Equation 1 describes how the variance of the data distribution exponentially decreases across t generations. The higher the value of gamma, the faster the collapse of diversity. Equation 2 describes how the mean of distribution changes less as variance shrinks, eventually leading to a delta function. The mu minus 1 over mu term establishes an asymptote to ensure perplexity never falls below 1.
If we solve this first differential equation in terms of as a function of t for variance, function of t generation, and we solve the second equation numerically as it's nonlinear using MATLAB's ODE45 solver, plot those two solutions so we get the top graph where it's plotted against generation t. And the behavior makes sense because we see the variance collapse down to zero in the large number of generations, and we see the mean stabilize at some value. And our parameters are there based off some arbitrarily assigned possible data set. Now we can plug those solutions back into the formula for the Gaussian distribution, and we get the plot below. And analyzing its behavior, we see convergence to a delta function for a high number of generations in purple. What's interesting here is that given the function of variance in terms of t, we can solve for the number of generations it takes for the collapse to occur. So we have to define what collapse practically means. So we set epsilon, some value between 0 and 1, to be the threshold for collapse. And we're able to predict the number of generations it takes for the collapse to occur. So the results are that the model converges to a delta function, and we're able to predict the number of generations it takes for the collapse to occur. On to the next model. It's the same as the previous one. The only difference is that we have rho, which is the fixed proportion of a data set that's human. The two terms, variation naught minus variation squared and mu naught minus mu, are the restoration terms. So essentially what they do is that if the variation is above or below the original data set, and if the mean is above or below the original data set, those terms pull in the variation or the mean to be closer to the original human data set level. And eta and beta are the parameters that help describe the strength of that restoration. Very similar to as we did before, if we solve that first differential equation as variation as a function of t, and we solve the second one numerically using MATLAB's ODE45 solver, then we can plug the solutions into the Gaussian formula to get the plots below. Each one of those plots representing different values of rho being a predetermined fixed value of human data. And watching its behavior, we see that as we get greater and greater values of rho, the data sets become closer and closer to the blue, which is the original data set. And we see rho equals 1, basically means the entire data set is human. We see the two data sets are basically identical, which makes sense because rho represents the amount of human data in the sample. And what's interesting is that for any non-zero value of rho, we reach a steady state solution. So that means we've not converged to a delta solution, but rather we're able to predict exactly what the distribution is going to look like in the long run if we know all the values for parameters and we know the value of rho. And the higher value rho, the closer to the original distribution we are.
The third model represents how two AI systems, AI A and AI B, interact and update their understanding based on what the other produces. The differential equations show how the two models synchronize and start producing nearly identical outputs. The rate of synchronization is represented by kappa, and there are values of sigma sub b squared, sigma a squared minus sigma b squared, mu b minus mu a, and mu a minus mu b, which are acting to give both distributions the same variation and same mean. The equations 5 and 6 are solved analytically, similar to equations 1 and 3, and the equations 7 and 8 are solved numerically, similar to that of equations 2 and 4 using ODE 45. These graphs visualize the outcome of the prior differential equations. The solid lines represent the AIA and the dashed lines represent AIB. They show the differences in perplexity and synchronization based on differing kappa values. In conclusion, will the quality of AI model results dramatically decline, slowly decline, or remain unaffected? The quality of AI model results will decline based upon the parameters of lambda and alpha, which represents the rate of variance collapse and the rate of mean collapse. If those parameters are known, we can calculate how long it takes for model collapse to occur using the formula, which represents generation of collapse to the logarithm of epsilon divided by the rate of variance collapse. Can human data slow, stop, or reverse the rate of collapse? The presence of human data can prevent this model collapse as it leads to a steady state solution, which prevents the convergence to the delta function. And what is the role of multiple AI models interacting with each other's outputs? Multiple AI models cause a convergence to two identical data sets upon interacting with each other's data sets. The limitations associated with this model include assignment of arbitrary values of parameters. To verify the accuracy of these models, these parameters would need to be fitted based upon the behavior of an AI model. Also, the assumption of normality is not true for all data sets, so this model cannot be applied to non-normal data sets.